Hey guys, back at it again. We're trying for our second flipped classroom lesson. Again, it's just a little lesson that I think we'd be best served to try it this way and save us a little bit of time. But we're graphing. We're talking about sine, cosine. We did the simple ones, and so now I'm going to start to ratchet it up just a little bit. We're going to crank it up just a couple of notches, and we'll see how we do. So before we can get started with this, we need a little prerequisite skill. There's something I want to go over with you guys before we get into the teeth of this. So I'm going to open up Desmos here, and we are going to take a look at some things. So here's a Desmos I've already made for us. It's just a parent function, a quadratic. Hopefully you've seen this somewhere in your math lives before. Just y equals x squared. Notice we're going to focus on this beginning point here, this minimum here of 0, 0. For my next graph, I'm going to click this x minus 3 squared. Our intuition tells us with a minus 3 right here, okay, the negatives go to the left, so maybe this whole graph might move to the left, right? It's a horizontal translation. When we click on it, though, it's not the case. It's counterintuitive, okay? And x minus 3 squared actually moves every single one of these points to the right 3 units, okay? If we focus back on that first point, if I plug in a 0 on our first one, 0 squared is 0, and that's where that's coming from. On my second one, if I wanted that same output of a 0, I can't plug in a negative 3, right? To the left, we would think negative 3. We would actually have to counteract this minus 3 by putting in a plus 3, because 3 minus 3 is 0, and then 0 squared is our 0 we're looking for. So inside of our function, before we square anything, we're changing this x coordinate we're putting in. When it says a minus 3 on the inside, that actually moves it to the right. So we can take it one step further. Where would x minus 7 squared move us? Just further to the right. Notice every single one of these points gets moved 7 units to the right. This point gets moved over here. Every one of the points just gets shifted, okay? And in the same respect, x plus 3 squared, intuition says right 3, it isn't. X plus 3 inside of our function with a plus 3 is actually going to move this pink, every one of these points, that pink line, to the left 3 units. And there he is. Plus 8 would move it to the left 8, so on and so forth. And it doesn't just work for squared. I did another parent function. Here's a square root function, y equals x squared, or the square root of x, with a minus 4 down here inside of my function. That's actually to the right 4. Click on it. There, all these points got moved to the right 4. X plus 3, move us to the left 3. Yep, there it is, left 3. So that's just our little prerequisite skill, keep in the back of our head when we are dealing with translations, when we're sliding graphs around, changing these x coordinates. It's actually going to move it the opposite way we think it might. Or maybe you remember this from Algebra 2 days and we knew which way it was going to move. But that's what we're going to tackle today. Let's go ahead and take a look at, do a couple of example problems. So let's switch this over. Attempt to switch this over, obviously. There we go. Still, let's stop. Technology, still getting the hang of it, but I got it going now. We are back. So we're at our notes here. This is, it says number 2 because it's just a continuation of the notes we did earlier, but notice what we had talked about. This is actually graphing now, y equals 1/2 sine of x minus pi over 3. We haven't had to deal with this yet, but thinking back to our prerequisite skill we just looked at a couple seconds ago, I'm taking the sine of this entire thing that's inside my function. X minus pi over 3 is actually going to move every single one of my points from my typical sine curve right pi over 3 units. Okay, to get this done, to graph one period of this, nothing changes at first. Okay, at first we do exactly what we did with the simple ones, and that's to find the period. To find the period of our function, it's always going to be 2 pi over b. B is always that number that's going to be in front of our x value or t value or whatever variable we're using, but in this case it's an x, and there's an invisible 1 there. b is 1. So 2 pi over 1, easy enough, that's 2 pi. That's going to be my period. Next step from there, once we've decided on the period, we want to break it up into fourths. We take half of that, so I'm starting at 0. Going down to 2 pi, that's going to give me 1 period. We find half of 2 pi, which is 1 pi. We take half of that, which is pi over 2. And then we take 3 of those. Half of that, 3 of those. So 1 pi over 2. This would be 2 pi over 2. The next one will be 3 pi over 2. Remember, I'm giving you these key values for a sine curve. I'm always going to put you on the cardinal directions. So we don't have to know the entire unit circle again. We just need those special points, the easy ones, right? The northeast, southwest, the zeros and the ones, the maxes, the mins, and those midpoints, the nodes and antinodes. So normally, from this step right here, we would just start ripping these guys in, these x values, into our function and seeing what they kick out, what y value, and then graphing them. But Mr. Edward, wait a second. If you put a 0 into this function, 0 minus pi over 3 is negative pi over 3, and I'm trying to take the sine of negative pi over 3, yes, we can do that, but that's not a northeast, southwest point. I know it isn't, because we're not there yet. Okay, this was what we normally do. What we have to do from this point is account for the fact we're moving all of our x points to the right, pi over 3, which means we have to move all of these key values that we used to use on a simple one, we have to move those over pi over 3 by doing the opposite. The opposite of a minus pi over 3 is a plus pi over 3. We're going to add a pi over 3 to all of those things. So here is a lot of the same stuff I said. This translation we're talking about in regular function land, that's horizontal translations, vertical translations, but here in function land, when we're here in trig land, when we're graphing sines and cosines, we call it a phase shift, okay, where we're changing the phase, where we're shifting it over to the left or right. So typical values, usually those would be the ones we use, but because of this thing, this phase shift, we're going to add pi over 3 to all of these values. So again, let's see what that looks like. I have typical values, adding pi over 3 to all my typical values, okay, and then it's going to take some fraction work, but we can handle that. We are in a higher math class, so 0 plus pi over 3, that's simple enough. That's just pi over 3. If you go through now and plug pi over 3 into our function, pi over 3 minus pi over 3, that's 0. Sine of 0, got to start getting good at that. Sine of the y coordinate, sine of 0 is 0. 0 times 1/2, 0. So I started initially by plugging in a pi over 3 here, and it kicked out a 0. That's where this point is coming from. Pi over 3, kicking out a 0. Okay, now we do the next one. Fractional stuff. Okay, that's 3 pi over 6. 2 pi over 6, if I got a common denominator. 3 pi over 6 plus 2 pi over 6. That's 5 pi over 6. Okay. If I plug a 5 pi over 6 in here, and you may have to write this out, and that's okay, but I'm going to skip some steps here. A 5 pi over 6 minus a 2 pi over 6, that'd be a 3 pi over 6. 3 pi over 6. We're going to think of 3, 6. That's pi over 2. Yeah, that's the north line. That's the top one. Good. The sine at pi over 2 is 1. 1 times a half is a half. Okay, so I originally plugged in 5 pi over 6. I ripped it through my function. It kicks out a half. Okay, the rest of them follow very similar. 3 pi over 3 plus 1 pi over 3. This one would be 9 pi over 6 plus 2 pi over 6, 11 pi over 6. This one would be 6 pi over 3 plus 1 pi over 3, 7 pi over 3. Again, we seek patterns. We seek to find patterns with this stuff, but we would get then 0. It's a sine curve. Starts from the node and then goes up to the antinode, back to the node, down to the minimum, back to the middle again. Okay, I'm bouncing back and forth between these vocab words. So we have our points. That would be 1 period. Fantastic. We could plot those, and we've done what we set out to do, which was graph 1 period of y equals 1/2 sine x minus pi over 3. But I want to take you guys through the process, the pattern seeking. So I put down here our initial, those values we got, those special x coordinates we're going to use. And I put them in terms of pi over 6, just so we can find the pattern. And there's always going to be a pattern to this stuff. periodic functions just keep repeating themselves over and over. So if we can figure out how they're repeating themselves, we can move that pattern on. Extrapolate is the word, but make that pattern continue. So if I change pi over 3 to pi over 6, common denominator, 2 pi over 6, 5 pi over 6, 8 pi over 6, 11 pi over 6, 14 pi over 6. If I wanted to do another period, like graph 2 periods, I would just continue that pattern. It's adding 3 each time. 17 pi over 6, 20 pi over 6, 23 pi over 6, 26 pi over 6. And I'm reducing my fractions when I start doing that. It's just a good habit to get into. So really, once we get good at these, and you guys will get good at these, just between the first two, if we can figure out what do I have to do to get from pi over 3 to 5 pi over 6, like how much am I adding, I can just keep adding that amount each time to get my next x values, and I don't have to go through this whole process every time. Okay, I can just say, oh, this is 2 pi over 6, this is 5 pi over 6, I'm adding 3 each time. Add 3, add 3, add 3. Okay, and I'm simplifying them, but it will be helpful, I promise. Okay, so we graph these things, put those dots out there. This is what it looks like. I know I said 1 period, but trust me, you're going to have to be able to graph 2 periods of these things as we keep going on. My first point was pi over 3, 0, node. 5 pi over 6, 1/2, antinode, node, antinode, node. Max, middle, min, middle, max, middle, min, middle. We're sitting pretty. That's it. That was the lesson, you guys. Tomorrow, I want you to come to class prepared. I want you to have tried this one. Okay, it's going to look pretty similar. We're going to do the opposite. We're going to find our normal x values that we would use if 2 pi over 1 using our 2 pi ones. Then to each one of those, we're going to subtract pi over 4. Do the opposite. Okay, you'll get these new key values. You'll plug them in one at a time. You'll rip it through sign, multiply it by 2, and then do 4 minus that. You'll get these values, and you'll plot 1 period. Let's do 1 period of this function right here. We'll try it out. So I look forward to seeing you guys tomorrow. We're moving on. We're moving ahead. See you later.